So I'm just going to go through a couple of tools here. Those tools, you should have them basically on every system. And this is not all they can do. I mean, as with any other tool you will encounter on a Linux box, this can do so much more. And I'm just going to scratch the surface and just going to show you a couple of things that it can do. So readelf is actually something that can read information about files in executable and linkable format, which basically means these are either shared libraries, so .so files, or executables that need shared libraries, so your actual program executable. So most programs today are executables and a bunch of shared libraries. That's usually how stuff is shipped today. So our example here is libmpi, because it's often something that you want to look into, like how is your MPI implementation, what is it using under the covers, or you want to change the MPI implementation. So I thought that that's a good example here. So if you look at readelf-d, just libmpi.so, it will tell you like three different types of entries. There's the needed entry, then there's SO name, and then there's RPATH. So first of all, needed. That really means this shared object depends on another shared object. So this is something the loader. So when you execute a file, it will actually go out, and the loader will actually try to find shared objects, and it will actually look for, okay, if I load libmpi.so, it will look for libopenrte.so .40.
And it's going to look through your LD library path to get that.
Because it needs that. Yeah, I'm going to go into those later. Like, where is it going to look? There are some default paths, and you can mess with that. But this is basically what it does here. So all it knows here is I need something, and it's called libopenrte.so.40. And you see, it's not called .so, but it's called .so.40. So there is a version information in here. And the same version information you will also see in its own name, like the SO name of this executable, of this shared object. It's also called so.40. So what this version information can tell you, if you're looking through this, is really just if this is binary compatible. Because so if you look at the actual file, like what is libmpi.so? libmpi.so is just a symbolic link. It's not a real file. But this links to something called so.40.30.5. But you can assume, as it's calling itself .40, that anything that is .40 is compatible to this version.
Hi. If you're enjoying this, can you click that like button? Seriously, it'll just take you like 1 second, not even that. And if you really like it, click on the subscribe button over there. We'll let you know next time we make something. Pretty easy, right? Yeah. Okay, back to the show.
So the next thing I want to talk about is a tool called nm. What you can do with nm is actually you list the symbols that are in an object file. Now, symbols, the easy way of thinking of symbols is really, it's either a function definition. So if you have a C code compiled and you actually have a function main in there, then main is going to be a symbol in that object file. Or it's a function call. So if you're calling something called main, it's also going to be in there, but the symbol is going to look different. So again, our example, mpi.so. And this time I'm just taking any MPI call. I'm just taking MPI all reduce in this case. And if I'm running nm on this, I see there's actually two symbols for MPI all reduce in here. There's a weak symbol, and then there's a text symbol in here. And the weak symbol is MPI all reduce. That is the one that you usually call. And the text symbol is pMPI all reduce. Now, the interesting part here is text in this case means that is really defined. That is really, so if you look up the code for OpenMPI, you will find pMPI all reduce as an actual function that does things. But MPI all reduce, its weak symbol, you can think of as something like a pointer. So this points to MPI all reduce. This is something we're going to come into later because that's something you can make use of. And that's something a lot of people make use of, especially in the case of MPI. The second thing you can see in here is, and M will also tell you what is used, what needs to be defined in a library. So in this case, we're going to look for get hostname. Get hostname is not something that is actually defined in MPI. It's not implemented there. It's implemented somewhere else. So it is a symbol in there in the sense that it is being called, but it's undefined. So it has to be defined somewhere else. And well, there's a hint here in the name where it's going to be defined. It's probably going to be in glibc. And there's another interesting part in here, which is this @@ thing, which is basically something like a tag, and that's usually used as version numbers. So inside of wherever get hostname is defined, there could be multiple get hostnames defined with different version numbers. And the question is, like, you have to figure out, well, is that actually there? So you can look at libc.so and look for get hostname, and it's going to tell you, yes, of course, it's a weak symbol, it's there. So you know it is defined in there, but you don't know which version is actually defined in there. Do I actually get the version glibc_2.2.5 or not? And that's where the next tool comes in. So if you want to know where whether or not that version is actually defined in here, you can look at strings, right? Strings basically just tells you, if you run strings on a binary, it will just spit out everything that is kind of readable for a human. So everything that looks like an ASCII character, it would just spit out. And you can grep through that. So if you actually do strings on libc.so and you grep for everything, every line that starts with glibc, you'll actually see, okay, 2.2.5 and 2.2.6 is defined in here. So that's how you figure those out. There's just one thing about glibc, just for completeness here. glibc, it's the only library that I know of that you can actually execute. So you can just run it. And what it will tell you is basically its version.
That's like a really weird Easter egg.
Yeah.
How did I get this far in my life as a geek and I didn't know this?
Okay, again, we start with OpenMPI. And we want to figure out OpenMPI, when does it actually call libfabric? Because that's something we use a lot. So that's something we're interested in. Okay, so FIOpen, like one of the first libfabric calls that you would ever see or use. Which version is actually expected? This is not in libMPI. It's one of the other OpenMPI libraries, but that doesn't matter in this case. This is still inside of OpenMPI. So if you take NM and look at this OpenMPI library and look for FIOpen, you see, okay, it's undefined. So it wants to call this. It calls it somewhere, and it wants fabric version 1.5. Right? So then the next thing you want to know is which libfabric version does this library actually use, right? So in the beginning we have this needed entries, and you can run LDD, which basically
looks for the dependencies.
Looks for this needed entry for you. And if you run that, you will see, oh, okay, this is also in /op/amazon.efa. This is the default path. Does that actually have the correct version? Is that actually fabric version 1.5 in there? So you do an NM on that, and you look and then say, oh, no symbols. Damn. So what do? That can happen, and it happens a lot to like low-level libraries, because if you strip up the symbols, that's something you can do when building the shared object. It will actually make it smaller, which is better if it's something that has to be in memory all the time. So that's why people do that and strip off the symbol. So it's still machine readable, but it's not human readable anymore. But you can run strings. So if you run strings on this and you grep for fabric underscore, you will see, okay, these are all the versions that are supported here. So I'm good. Fabric 1.5 is actually in here. Okay, object dump. So this is actually if you want to do some deeper debugging. So now we figured out in the last part where are calls resolved and how are inter-library calls, like from one library to the next or from the executable to the library, how do those get resolved and how do they match and all of that. But now if you have calls within the same library, you have a couple of different object files and have been linked into the same libraries and there's calls in between, which is like bread and butter of every program. How do you actually look at that if you cannot actually look at the source code? And that's where something like object dump comes in, where you can read something that kind of looks like assembler. This is probably wrong, but this is what it looks like. And it is, you can make it out. It's good enough for you to actually see and actually read where do those calls actually go. What you want to know is where's the FI version in this case. FI version is the call that we're looking for. Where is that actually called? So you open up, what you usually do is you run nm on the library and you pipe that into less or whatever text editor, and then you look in there. So you see there's a function defined FI version at PLT, and what this function actually does in the first line is a jump, which is basically a function call to some memory address here, and this has been located as, okay, this is the FI version call. So here's where FI version is actually called. And this FI version at PLT is like a wrapper function around this, because it's really just these 3 lines. There's no more to that. So we're still figuring out, okay, we now it's kind of wrapped, but okay, where is FI version at PLT then called? And if you trace that, you will see FI version at PLT is actually called in another function called opal common OFI MCI register. That's something internal to OpenMPI, but that's just how you can actually find out where are which function calls in there if you don't have the source. In this case, we actually do have the source, so we can look it up. So if we actually look up the same symbol again, same opal common OFI MCI register, you will see actually the first function call in here is FI version. Now we have a couple of tools now which we can use to actually navigate our way inside binaries and from one binary to the other. So there's one more part missing, which we're going to go into the next session, and that is actually how do those interlibrary dependencies work out. So in things of static linking, dynamic linking, RPATH, RUNPATH, all of those things. And once we have all of that together, then we can go into now using all of this in the real world with actual binaries that have been shipped and where we have to change some things without access to the source code.
If you enjoyed this tech short, please give us a like and consider subscribing to the channel. If there's a topic you want us to focus on, reach out to us at askhpc@amazon.com. We want to make it easier for scientists and engineers to solve the world's hardest problems. We think the cloud can help by giving them access to powerful tools of any shape and size whenever they need them. And that's where you come in. Let us know what you need. We'll see you next time.